Who?
Good morning, ladies and gentlemen. Okay, today we're going to be talking about current. And we mentioned current yesterday.
Yep.
Right? So current is the amount of charge flowing per second. Coulomb over time.
It's coulombs per second, and the derived unit is an ampere.
Over second.
It's an ampere or an amp, and the ampere is the unit of current, and amps.
Let's rock and roll. Okay, so how do we draw this ampere, this amp, okay? How do we draw an ammeter within a circuit? So an ammeter measures the current. It looks like this. Okay,
All right, now
it's just.
Don't you?
No.
Well,
okay.
actually, you've seen it.
It looks like this, but it measures something different.
Yeah, and do you want to have to draw a picture of this? No, especially a lot of scientists and physicists and electricians who don't have the art skills, and so you just make a circle.
With an A.
That's it.
In it. Okay, so it must be part of the circuit in the flow.
If you're going to measure the flow, it's got to be in the flow.
Makes sense, right? Okay, so draw a simple circuit with a bulb, a battery, and an ammeter.
So
Ammeter.
yesterday we gave you the symbols. Let's go back to them.
So here's our battery. I'm gonna put my bulb here. Okay, and then I'll put my ammeter right there.
Yeah. Okay. Now, which is the short side? Which is the long side of your battery? I'm having a hard time.
That's my short side right there.
And don't those wires in the bulb connect to the wires that you've drawn?
Wait, say that one more time?
See, you've got the little loop inside. They should be connected.
Burp, burp, like that. Thank you,
Yeah,
sir.
because if they're not connected, you ain't got no circuit. And that's it.
That's it. Was I doing anything else? Okay, so make a simple circuit. Make a simple circuit with a bulb, a battery, and an ammeter. Flow the current and observe.
So if you were in the classroom, you'd be doing this yourself right now.
Okay, so this is our bulb base.
Yeah.
And so what we have here is, what do we talk about? How it comes in, how we're gonna clip it here. This is one of our inputs right here.
Yeah. Well, on the bulb, you've got. Take this out. I'll let you do that.
Okay, on the bulb, you can actually see what we got. Two wires coming in, right? We have a wire. It's hard to hold this thing. This wire comes out this side, and the other wire goes down all the way.
Touches
right
the side.
And you can see.
And the other one touches the bottom. Remember, light the bulb.
Yeah, light the bulb.
So one side is on the bottom, one side, and that's what this base is for.
Yeah, you can see where it was cauterized at, and so the base holds that and
you can see on one
that.
side. Here, let me see this. It connects with the
bottom right there.
the side.
Oh, is that the side?
And then on the other side, it connects to the bottom.
Oh, there we go. That's what I was trying to say. Yeah. Look at that. Well designed. Okay.
It's a simple thing.
It is a simple thing. Okay, is that in good?
Yep.
All right. So, and then, should we show them the trick? Or
No,
is that only for the
that's
classroom?
when you're in class and dealing with them.
Well,
we wish you were in
next time.
class. We wish we were dealing with you, but.
Okay, so let's see. What are we gonna do again?
Well, you're gonna hook
We're gonna
up.
make a simple circuit with
You're
a
gonna
battery.
hook up the bulb, a battery.
Okay, so here we go. So I'm gonna hook up this to this side.
One side of the ammeter.
Okay, so this is my ammeter. This is my battery. This is my bulb. That means I need to hook up something here.
Okay, now these wires, the color of the wires doesn't matter. They're all conductors on the inside. It's metal.
Okay, so we've got it going. We're gonna have it going. I'm gonna flip it this way here, so I have my negative side. So we're gonna go out of the negative.
Well, just hook it up and
over
flow
here.
and see what happens.
And then, I'm in the way here. Okay, what do we see happen? Okay.
The bulb lights up, and the ammeter registers some current.
What would you call that?
Well, it's about 190 milliamps.
Okay, I'm actually gonna write that up here.
So I equals
190 milliamps.
Wait a minute. Now, what's a milliamp? That's 1,000th of an amp, right?
Yeah, so I would just divide it by 1,000 to get.
Or move the decimal 3 places.
Yeah, 1, 2, 3.
Yeah.
Okay, so we've really got 0.190 amps of current.
Amperes,
here.
that's right.
Amperes, yeah.
Amps is good.
Okay. So let's go ahead and add a second battery. How about that? Okay.
Oh, well, first of all, with the first battery, turn it around.
Oh yeah, that's right.
Let's see what
Okay,
happens.
so before it was like this. Okay. If I flip it like this. Ooh,
Oh, notice what the ammeter does?
what's going on there?
Yeah, that's a good question. What is going on there?
Okay, well, so we flipped the battery, which means we
Well,
flipped
turn
the
it back
flow.
around. Both times the bulb lights, but the direction of the needle on the ammeter is
Yeah.
different. And why?
So electrons are flowing, but the Y has to, because we flipped the battery, the electrons are flowing in the opposite direction.
Yeah, so an electron is going to be repelled from the negative and attracted to the positive. So which direction current flows depends on how you got the battery hooked up.
Yeah, and so, Boykin, you were telling me some ammeters have a zero in the middle.
Zero in the middle, so you can measure in either direction.
Yeah, and you could measure in either direction. And also, I don't know if we talked about this in this video or in the last one, maybe for regular physics, but we're plugged into the middle one here. 1, 2, 3, and there's 1, 2, 3 options here.
There's 3 scales on here, and the posts, this is 550. And we're plugged into the 500, so that's the top scale. So we're reading off the top scale here.
Yeah, yeah. Are we ever gonna have one? Why are we using this one instead
Well,
of that?
if you have 1 amp, if you've got 1 ampere of current traveling through your body, it will kill you. Your heart will stop.
Okay, so make a simple
We've already- yeah.
circuit. We're good with this. Oh, we didn't put the second battery in. Okay.
I interrupted you. Sorry.
Okay, so here we go. Oops, something that must be.
Make sure the bulb's screwed
Oh.
in.
Huh? Did it just die on us?
Here, try it with 1.
Oh, that battery. Oh. Oh, there we go. They just weren't all together, I guess. Okay, so what do we see? Well, first of all, let's take a look at the light.
The light is brighter,
Uh-huh.
and before we had 190 milliamps. Now we've got more than 200 milliamps.
Okay,
so
so
there's
it-
more current.
It increased. Oh, I don't think I was pushing in the right putting it in the right spot up there. I think it was maybe down here or something. I don't know. Okay, so more battery, more juice, more light. Is that right?
Juice, the technical term.
Okay, so we've made our simple circuit, and we know that if we add a second battery, we had more current, and also the light was brighter.
Yeah, so we recorded the data from your circuit. We haven't put in which direction electrons are
Oh
flowing.
yeah, we didn't do that yet. So, well, we know that this is the negative. We know that this is the positive side over here. And we know that if this is positive, that's negative. Electrons are going to be repelled from this side and attracted to this side. So that's how they're going to be
That's the
flowing through.
direction current flows.
Okay. Okay, just a reminder. Our current is going to be the charge divided by the time.
That's right. That's the definition of electrical current. It's how much charge per second is flowing.
Yeah. Okay, so let me go ahead and write that on the board. Okay. So we said current is charge over time.
Yep.
Connect the circuit and run the current for 3 seconds.
I think it's just one battery.
One battery.
So we're just take your mark, get set.
Oh, sorry. What? I can't get it. Mark, it's set. 1 Mississippi, 2 Mississippi, 3 Mississippi.
Okay, 3
Okay.
seconds.
And how many coulombs of charge went through the bulb? Okay, so coulombs is going to be this one right here, right?
Yeah.
So we're going to multiply by T. Okay, so we need time, which is
TI or it. It.
it, or TI is a rapper, so that works.
There
for
you
me.
go.
3 seconds times, and how many amps did we have the whole time?
0.190.
0.190 amps. Okay, so how much charge? 3 times 0.190 amps.
0.5 something.
0.57 coulombs. Coulombs. Okay.
See how simple that is? So you run it for 3 seconds. At 0.190 amps, you're running 0.57 coulombs of charge through that battery.
Sweet. Oh, what's on the next slide here? Okay, so add a second battery. What is the difference? So 3 seconds again. Okay, ready? And 1 Mississippi, 2 Mississippi, 3 Mississippi.
Okay, that was about 270 milliamps or 0.270 amps.
Okay, so 0.270 amps, you said?
Yeah.
And we did it for,
Times 3 seconds.
we did it for 3 seconds, all right? Okay.
Yeah.
Okay.
That's going to be about 80.8.
So 0.270, 0.81.
Woohoo!
Okay, so
We're running more coulombs of charge through there.
the more battery we had, the more the amps were.
Now
and the more
and
coulombs.
you may expect there to be twice as much, and there should be, but we'll talk about why there's not as we go forward.
Oh, wait, over here. Sorry, I keep going back over there.
That's all right.
All right, so a cell phone.
Did we miss
charger.
something?
Nope, that's our next slide right here.
Doesn't it say what do you do when you charge your cell phone?
Nope, that's gonna be over here.
Oh, sorry. Thank you.
Next slide, next slide. Okay, so a cell phone charger is plugged in for 25 minutes and transfers 300 coulombs of charge. How much current flowed?
Well, current is coulombs per second, so we're going to need to know how many seconds in 25 minutes.
Okay, so we want to know how much current, and we want coulombs over time, and we have 25 minutes, you say?
Yeah.
Okay, so I can just multiply that by 60 seconds, right?
Should be 1,500.
1,500.
Woohoo!
Woohoo! Okay, 1,500 seconds, so that's my time. And then how much charge does it run through?
300 coulombs.
300 coulombs. So 300 divided by 1,500, I get 0.2 amps.
0.2 amperes. 0.2 amps.
Okay, so how much current is flowing through when you charge your cell phone for 25 minutes if it transfers 300 coulombs of charge? 0.2 amps. Do we want to show them the...
Well, we're
later?
almost there.
Okay.
We're almost
We're
there.
jumping the gun here. Okay, so what are you doing when you charge your cell phone?
Well, you're like charging it, aren't you?
Right? Like you're just charging it up so it's got the battery. Okay? All right, let's take a look at this equation here. So in a battery, there's a chemical reaction happening. So the chemical reaction that puts the electron at the negative pole is this electron right here. Okay, that electron that gets kicked up and is moving through that circuit.
Yeah.
So how do we get that electron? How do we get it kicked out over here?
Okay, now this is just a general formula. It doesn't have the actual chemical species.
Yeah, we don't actually call it A and B in there. It's some
like sodium and chloride,
yeah,
but it's
some
not.
other stuff, okay? But we're gonna represent it, so you've got this compound that we're gonna represent as A, and then this anion, it's just a negatively charged ion here.
Yeah.
And what happens is they combine,
Yep.
right? And when these two combine, that negative gets kicked off in the form of, it's an electron basically.
Yeah, and that comes out the negative side of the battery at the same time.
Now at the positive pole, now we're talking about over here now.
On the positive side.
Okay, that electron has done its thing. Okay, that electron is coming into the battery, if you will.
Yeah.
And at that end of the battery, you have these two compounds.
Yeah.
Okay, and what happens is the D and the C combine right here, kicking off B plus. That electron combines there to make.
So the electron comes in, these two things combine and spits out the B minus. And what happens to the B minus?
Well.
And it's like a bicycle chain. It's not like one goes through the whole thing. As one electron comes in, another electron goes out, and around the circle, it's like a bicycle chain of electrons moving through the circuit.
It's kind of like it's being recycled through. I don't know if that's the right
Cycled
terminology.
through.
Yeah, not I guess cycled through. Yeah,
Yep.
bicycle. Okay. And so what's happening when?
And this is like when batteries go dead, all the products all the reactants are used up,
yeah, these guys right here.
and all you have is the reactants, and you got to throw the thing out unless you have a rechargeable battery.
which we do with our cell phone.
That's right. It's rechargeable.
Yeah, thank goodness, right? Or else you have to buy a new one every day.
So what does recharge mean?
So recharge just means that basically we're going to be going the opposite direction.
Turn those arrows around.
Turn those arrows around, and we're starting off with our compound and with this anion.
Yeah, well, instead of having the electron come out, you're shoving electrons in, and what does that do?
What does it do, Boykin?
Well, it breaks up the AB,
And we're left with this guy right here, and then
and when that B minus is present at the other end,
we can go back through this way and shove that electron, basically making it go through the other way.
and so what the charger does is it pulls electrons out the positive side of the battery and shoves electrons in the negative side. Shoves them in backwards, pulls them out backwards.
So basically, this whole thing going forward, if you got that, it's basically reversed for that, for
Yeah.
when you're charging.
And so what it does is it replenishes the reactance so that when you take your charger off, it can go in the normal way and your cell phone works.
It's a good thing.
Woohoo!
Okay, so a cell phone battery is rated at 2200 milliamps hours.
Milliamp hours, that's
What
right.
does that
What does that even mean? Now, there was a time, boys and girls, when cell phones had removable batteries. They're not built that way because they want you to buy a new cell phone.
I used to have one of those.
I know.
Okay, so this is really just current, right?
Yeah, amperes, milliamps are current, and
this
hours is time.
Time.
That looks like it. Wait a minute, that's it.
It or TI. So it is
right.
going to be right here, right? And that's going to be equal to the charge.
Yeah.
It right here. Q
Yep.
charge. Okay. And so what's really going on here?
Well, a milliamp hour is the unit of charge. So what is the other unit of charge that we've been using?
A
Coulomb.
right?
Yeah, and that
So-
should be a Q instead of
Q?
a C.
Oh, sorry. Yeah. the unit.
But you were right. The units are
Or
coulombs.
No test charge.
Yeah.
Okay, so what is this really telling us? It's telling us the quantity of charge that is going to be put into our, flowing through our charger into our phone.
Yeah. So what you've got is if you have more milliamp hours, that's a bigger battery. It can store more charge. It'll go longer before it runs out. Less milliamp hours is less charge, and it'll run out sooner.
So you want a battery that has a higher number here,
Yeah.
okay?
Unless you want a big old fat cell phone that takes up too much space in your pocket.
I know. What do you? There's the pros and the cons here. Okay, so if your charger is rated at 0.3 amps, I need a new color here. If your charger is rated at 0.3 amps, how long will it take to fully charge a half charge?
Half charge. So half
That
charge
many
is going to be 1100, right? If it's half charged, it's half of 2200. So that'd be 1100 milliamp hours. That's 1100 coulombs.
Right? Okay, so that's 1100 coulombs right there. If your charger is rated at 0.3 amps, the question is how much time will it take to charge it if you're trying to recharge
So what's that equation? Oh, there's the equation
right here, so we can just flip-flop these, right?
Yeah, and that C on top should be a Q.
Oh, I didn't even realize I was doing that.
I didn't either.
Yeah, Q. Sorry, you guys. Did I do that anywhere else? No, I just right there. Yeah, okay. All right, so that means 1100 coulombs divided by, we're going to do 0.3 amps. Okay. Let's
And
do
this our units will be seconds.
100 divided by 0.3. And it's going to be 3,667 seconds.
Well, multiply that times 60. 36, how much? 3,670 seconds?
Yeah.
Okay, divide that by 60. How many minutes is that going to
Oh,
be?
I like that. Okay. About 61 minutes.
That's an hour.
Yeah.
That's too long.
Okay.
What about their cell phone chargers? I think
Yeah.
now would be the time to talk about the rating on it.
So if you let's see if they can see that. Can you focus on it right there?
It's
Let's
too
see.
small. You're not.
Okay,
gonna see
so
it.
it says that it says 1 amp on it.
Yeah.
And so this charger is rated at 0.3 amps. This one is rated at 1 amp. And why is that a good thing?
Well, that's coulombs per, that's 1 coulomb per second. It'll charge it faster.
Yeah, so I could do.
You don't think you need a
Oh
calculator?
yeah, the one. Sorry. So then 1100 divided by 60, and it's going to be 18 minutes, right?
Yeah.
So that's a lot faster. It's almost 3 times as fast.
Yep.
Is that right?
Yep.
Yeah.
And if you have a cell phone charger, probably on it somewhere will be the current rating.
Yeah. Check it out. What you
Find your cell phone charger, find where it says how many amperes, how many amps it's rated at.
Now, Boykin, you were telling me at one time, I'm going to erase some of this stuff, that the cell phones would catch on fire.
Well, and here's the thing, if you have, it's like some of the cell phone chargers like 2 amps, and in the early days, what are those batteries made of? They're lithium ion batteries. And have you ever noticed that sometimes after charging your cell phone, it's hot? Because there's energy it's not 100% efficient. And some batteries would get so hot that they would expand and crack open, air would get in, and they would catch fire.
Okay. All right, so you measure 84 milliamps in your circuit. How much charge flows through if you measure it for 15 seconds? Okay, well, I just need Phew! Okay, so this is our equation, right?
Yep.
So 0.084 amps. And for 15 seconds.
You see what she did there? She converted 84 milliamps to 0.084 amperes.
1, 2, 3.
Boom, 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 boom.
Bada boom. Okay, so 0.084 divided by 15, and I get 0.0056 amps. Bada boom. Is that right?
No, because we want to solve for Q.
How much charge? Oh, snappers.
So
We never make
we need
mistakes.
to do it.
Yeah, we're gonna do it equals the charge. Sorry.
Hey, we never make mistakes,
How much
never.
charge flows? I saw flows, but the amps don't go here, right?
Yeah.
So 0.084 amps times 15 seconds, and then we're gonna. Oh yeah, what the heck? Those units don't even make sense. Okay, 0.084 times 15, and that's more like it. That's a number. Okay, 1.26 coulombs.
Coulomb.
That is what we want. So how much charge flows through?
So your cell phone is an important part of your life, yes? And it's an electrical device,
It's an
yes?
extension of my body.
And you probably don't know much about what's going on inside, but now you're learning some more.
Okay, so what is a volt?
What is a volt?
We talked about this. A volt is the unit of electrical potential difference.
Why does it have the word difference in there?
Because it's the change from one side to the other.
Yep.
Right?
From one place to another, the difference in electrical potential energy.
Yeah. Okay. Add a voltmeter wired across the bulb to your diagram. Should we do diagram first?
Yeah, here's a voltmeter, and instead, see, it's got the letter V on it, and instead of trying to draw this, it's just a circle with a V.
Yeah, and so we want to add it across the bulb, so that means we're going to add it right there.
Yeah.
Okay, so let's do that, I think. Oh, not yet. A volt is how many joules of potential energy difference for 1 coulomb of charge between one place and another. Okay, joules of energy, that's work,
Per.
coulomb of charge. That's just our definition.
Yep.
Right?
That's a volt, joules per coulomb.
Yeah. Okay, so electrical power. Now, should
Wait a minute.
we should do it.
I think
over
we
here.
should.
Yeah.
Let's play with it. Come on.
What are we doing? Come on, let's play. Okay, so we are just gonna add this. So here's our friend the voltmeter.
Here's our
And-
circuit.
And
With the ammeter's still there.
still doing
and
his
it's
thing.
just like our diagram.
And I'm just gonna add this in here. So does it pull it over too? Okay. Whenever it rains outside, do you ever hear that noise? It's kind of like a.
Oh, that's when the cars go by and the
it's kinda-
tires
It's kind of
make
like
that
nice.
sound.
Okay, so here's our voltmeter. We're all connected up, and we'll do one battery first. Okay, and let's see what we can find out.
give you a current. There's our 190 milliamps. That's about 1.3, 1.4 volts.
And then take a look at that bulb. So cute.
It's cute.
Okay, all right. So then, let's stick these two together.
The bulb is brighter.
Uh-huh.
We have more current, and now we've got more volts. It's about 1.7 volts. I beg your pardon, 2.7 volts.
And then how many, how many did you say? 2.7?
2.7, yeah. We're in the middle scale here.
Yep. Okay, cool. All right. So
if it's brighter, there's more light energy, there's more electrical energy, there's more electrical power. What the deuce is that?
what's going on? Okay. So electrical power is found by multiplying how much current is flowing across across how much potential difference.
Let's make some measurements.
Okay. So
And that's P is I
times delta
delta V.
Okay. So let's go ahead and take a look. Do you want to do one battery? Two
Let's
batteries?
use two.
Okay. One more battery. All right. So I think the amps were the same, right? Isn't that
That's about
2.7?
two,
Sorry, 270. Sorry.
270 milliamps. Write that down,
Okay.
270
Yeah,
milliamps.
you guys write it down. Okay, and
And
then
the
let's talk about our
volts
volts.
is 1.6. We'll call it 1.6.
1.6.
1.5, 1.6. So
Wait,
270.
the volts. Are we reading from the middle one right there?
Well, it's 3 volt in the battery, so that we're using the central scale here.
Uh-huh.
We're on the 3 volt post.
Yeah. Did you say 1.6?
Oh, I didn't mean to. I said 2.6.
2.6. 2.6.
Hey, I never make mistakes other than, of course, getting out of bed this morning.
Okay, so our volts were 2.6, right? Oh, sorry, our delta V.
Yeah.
And
And-
then our amperes were, this marker smells funny, very strong, 0.270 amps.
Amperes.
And if I want to get power,
You just multiply them.
I just multiply them. Okay, so power is going to equal 2.6 volts times 0.270 amperes. That's going to equal 2.6 times 0.270.
Yeah.
And I get 0.702.
Point.
We'll call it 0.7. 0.7. And what is
That's
my unit
volts
for?
times amps. Volts times amps. Let's see, what is a volt? That's a joule per coulomb. Volt is a joule per coulomb, and an ampere is a coulomb per second. So a volt ampere is a joule per second, which is a what?
What? Right? It's a what? Okay, so we did that. We nailed it. Okay. Oh, conventional current. Okay.
It is embarrassing to have to talk about this, but conventional current assumes that positive charge carriers are moving in the wires. I'm not making this up.
So what does that mean, positive charge carriers, Mr. Boykin?
Well, instead of what's actually going on with electrons, you can see here this I, this conventional current. Here's the positive part, and they've got something leaving the positive part and going into the negative pole of the battery. So that would be a positive thing repelled from a positive, goes that way, and a positive thing be attracted to the negative. And so in textbooks, you will find conventional current, the boys and
Should have
girls.
this one too. Didn't we have it on here? No, maybe we didn't.
Yeah, we did. Yeah, it's
Nah.
it's there.
So what does that mean? Well, so what we're saying is we know as long as you understand that electrons are what's really traveling and not protons.
Yeah.
You know, this is the way that the electrons flow. However, if I was to ask you to do this, to make a diagram using your proper symbols of your current, including a battery, a bulb, an ammeter, a voltmeter, wired correctly, show and label the direction of the conventional current.
So that'd be like what we've got right here. The conventional current.
And we go out of the positive and into the negative. I know.
Now here's why. We understood electricity before we knew what it was. The electron was discovered a little more than 100 years ago. But we've been dealing with electricity for about 200 years. And so they thought it was positive charge carriers moving in the wires, and then lo and behold, we discovered the electron.
Electron. But
And-
we know that's not true because the protons don't move, right? It's
And you
the
know how
electrons.
old people rule the world, and they say how
And they're like, yup.
that was the way I learned it. We're not changing, so sorry.
Okay, and that's it for today. And
All right.
no homework. Okay?
Sweet.
Yeah.